In this lesson, we're looking at a systems of equations by graphing, and in particular, solving systems of equations by graphing. And so the first thing we need to look at is what a system of equations is. Really, it's just a set of two or more equations, and really it's two or more equations that we're going to solve simultaneously. We're going to solve at the same time. All right. When we do that, basically the number of equations we have corresponds with the number of variables we have. So in these cases today, we're going to look at two equations. So therefore, two variables, x and y. All right. But again, it's just a set of two or more equations that we're going to solve simultaneously. The solution to a system of equations is a set of the values that makes all the equations in the system true. So again, that's all of the equations in the system have to be true. That's what makes a solution valid. All right. If it works for one of the equations, great. But if it doesn't work for the other, then it's not a solution to the system. All right. So it's got to be a solution for all of the equations, not just one. For example, when we look at this first one, if I want to determine whether or not the 4, 8, whether that ordered pair is a solution to the system, all I have to do is plug this in and see if it works. I'm gonna plug that into the first equation. So I plug the 8 in for y, and I plug the 4 in for x, and I see what I get. So I get 12 minus 4, so I get 8 equals 8, and 8 does indeed equal 8. So that gives me a true statement. So then I might ask the question, well, is that ordered pair 4, 8 a solution to the system? And the answer is I don't know yet. Okay, I don't know because, yeah, it worked for one of the equations, but for it to be a solution to the system, it has to work for all of the equations. So I have to plug it into this one as well. So I don't know until I plug it into both equations. So I plug the 8 in for y, and I plug the 4 in for x. And when I do that, I end up with 8 equals 8 again, which is a true statement. So now I can see that ordered pair worked for the first equation and the second equation. So this one is a solution to the system. So I'm going to say yes, this one is. Okay? It's the same thing with the next one. I want to know if this thing is a solution, so I'm going to plug it into the equation. So I have 3 times x, which is the 2, minus a negative 1 equals 7. And here this gives me a 6 minus a negative. That's like adding the opposite. So that's going to be a plus 1. So I end up with 7 equals 7, which once again is a true statement, but that doesn't tell me anything yet. I still don't know if this thing is a solution to the system. I have to plug it in to the other equation. So I'm going to plug it into the other equation. So let's see, I'm going to have x, which is the 2, plus 4 times the negative 1, and I want to see if that equals 11. It gives me a negative 2 instead. Let me see here. So I get negative 2 equals 11, which is a ridiculous statement. Of course, negative 2 does not equal a negative 11. Those are not equal. So therefore, this thing is not a solution to the system. Yeah, it worked for one of the equations, but it didn't work for the other. So the answer is no, this one's not a solution to the system. It has to work for all of the equations. I do the same thing with the next one. I'm just going to plug this guy in here. So I'm going to plug the 4 in for x, and I'm going to plug the 3 in for y. And I'm just going to simplify. That gives me 8 plus 3, which is an 11. So I get 11 equals 11. So it works for the first equation. I've got to plug it in still for the second equation because it has to work for both. It can't just work for one. So I get 4 plus 9, which indeed does give me a 13. So it works. All right. So since the ordered pair worked for both equations, I can say that yes, this one is a solution to the system because it worked for all of the equations in that system. All right. And this one again, I plug it in, so I'm going to plug it in. So let's see, I've got a negative 4 plus 2 times 5 equals 8, and I simplify. So I end up with 6 equals 8, which is ridiculous. 6 does not equal 8. So now from here, some of us might be tempted to plug this into the second equation, but why bother? Because remember, for this thing to be a solution to the system, it has to work for all of the equations. And right away, do I know right now that this will work for all of the equations? I know most certainly that it will not because it didn't work for the first one. I don't even need to bother plugging it into the second one because even if it does work for the second one, the answer is still no. Okay? So now systems by graphing. If I want to find the solution to a system of the system of equations, it's really just the intersection of these two lines. Okay, it's the point of intersection because when you think about what a line is basically a visual representation of all the ordered pairs that work for a particular equation. All right, And what happens if I graph all the ordered pairs for one equation, and then I graph all the ordered pairs for the other equation, the point of intersection is that one ordered pair that they have in common. In other words, the one set of values, the one ordered pair that works for both equations, okay? So here's what I do. I'm just going to graph each of these completely. So the first one has a y-intercept of -4 and a slope of 3. So I'm going to plot that y-intercept at -4. And the slope of 3, I go up 3 over 1. And I want some accuracy to this thing. So use a couple points when we plot that using that slope so we can draw a really nice line here. Because again, we want a little bit of accuracy here because I have to see where these intersect. The next one has a y-intercept of +4 and a slope of -1, so that's down 1 over 1. And again, I draw a couple of those points just to give myself a little bit of accuracy here. And now I look at where these two things intersect, and I can see the ordered pair here is 2, 2. So again, that's where these things intersect is right here. And when we look at that ordered pair, really what that's telling us is it's telling us the values of our variables. In other words, it's saying x equals 2 and y also equals 2. All right? And so what we're looking at here is basically when we solve any equation, I solve for the variable, I find out the value of the variable, and the same thing's happening here. I can just express those two variables as ordered pairs. It's telling me that x has to equal a 2 while y equals a 2 at the same time. All right? If I look at the next one, again, the y-intercept of that first example is a -5. And it's got a slope of 4, so it's up 4 over 1, up 4 over 1. And I keep going with that. Again, I want a little bit of accuracy with this thing because I have to see exactly where these two things intersect. And then the next one's got a y-intercept of 2 and a slope of 1/2. That's up 1 over 2. And right away we can see it as we start to plot these points. I can see that they intersect right here, and that's the ordered pair 2, 3. And again, I can leave my answer as an ordered pair, but think about what that means. It means that x equals 2, and at the same time, y equals 3. It's giving me the value of each variable, okay? In the next one, when I look at this guy, if I have an equation that's in this format, and I can't stress this enough, you can solve for y and put this in slope-intercept form, y equals mx plus b, but it's so much easier just to find the x and the y-intercept. If I were to ignore this piece, and say, all right, I'm going to solve this thing for y. I divide each side by 2, and I find out the y-intercept is -3. And then I do the same thing. I go back here, and I scribble out the y, and I solve for x. And that's my x-intercept. That's an x-intercept of a -2. And so what happens here, really, you should be able to do that in your head very quickly. But I get the y-intercept, and I get the x-intercept. And maybe I don't have quite enough in terms of the way in the way of accuracy, but I can see the slope. I'm going up 3 and over 2 each time, and I can continue that pattern. I can go up 3 over 2 again and up 3 over 2 again to make this thing a little bit more accurate. So even with just the x and y intercept, I can draw a pretty accurate graph because I immediately then can see the slope. All right. The next one has a y-intercept of 6 and a slope of 3/4, so I can go down 3 back 4 and down 3 back 4 again. And when I graph this thing, I get a line that looks like this. So now I can see this point of intersection. Here's where they intersect right here. It looks like the ordered pair -4, 3. Again, I can leave it as an ordered pair. That's a fine way to express this. It's saying that x equals -4 while y equals 3. If I look at the next one, I've got a y-intercept of 5, so I'm going to plot that, and I've got a slope of 2, so that's up 2 over 1 or down 2 back 1. And I draw my line, and then the next one has a y-intercept of -4 and a slope of 2. So that's up 2 over 1, up 2 over 1, or down 2 back 1. And when I graph these things, what I end up with is two parallel lines. And there's two things we should remember about parallel lines. First of all, parallel lines never intersect. All right? And since the system of equations, the solution is where they intersect, and these never intersect, it means I have no solution. So the answer is no solution here. The second thing we should always remember about parallel lines is that parallel lines always have the same slope. So when I look at these guys, because I have the same slope, I know I'm dealing with parallel lines. I could go right to saying no solution. The only thing I have to watch out for is if I were to scribble this out, if this was like +5 instead, so I had y equals 2x plus 5 and y equals 2x plus 5, that one's clearly not going to be no solution because it's the same line. So all of their solutions they would have in common. All right, so watch out for that situation versus parallel lines, which is no solution. Okay, and then if I look at this last one, I've got the y-intercept of -2, and I've got a slope of 1/2. It's up 1 over 2, up 1 over 2, or down 1 back 2. And again, I graph this thing, so I graph my line. And now the next one, again, I'm going to do x and y-intercept. Right here I can see the y-intercept is a -2. I do the same thing. I scribble out the y. And I solve for x. If I divide each side by the -1, I find out that x equals a +4. So really quickly, and again, we don't necessarily have to write those out. I'm going to do this in a different color. -2 and a +4 for my x and y intercept. And so when I graph this line, what I end up seeing is that I've got one line on top of the other line. So the question is, where do they intersect? And the answer is everywhere. They're intersecting the entire time. So every solution that they have ends up being a solution to the system. The problem is our temptation here is just to write all real numbers, which doesn't really sum up what's happening here. All real numbers, you're almost implying that any real number of x can go with any real number of y, which isn't true. Like the ordered pair 0, 0 here, that's not a solution to this system. Or 1, 1, or -3, 4. There's a lot of values here that are not solutions. Yeah, we have all real numbers for x and we have all real numbers for y, but it's very specific combinations of each of those real numbers. Okay, things like the ordered pair 0, -2, or the ordered pair 2, -1, or the ordered pair 4, 0. They're very specific combinations of those real numbers of x and real numbers of y. So instead of actually listing the solutions like we would when we had one variable and just saying all real numbers, what we just simply say here is that there's an infinite number of solutions. And I'm going to use the infinity symbol. And I'm going to abbreviate the word solutions and call it this, infinite solutions. So there's an infinite number of solutions versus something that has no solution. Okay?